Good morning, everyone. Welcome to our session. I'm Praveen Yalagandula with AVI Networks. Today, I'm going to talk about how to make your LBaaS a badass. And badass, by which we mean beyond application delivery as a service. And our goal is to make an enterprise-grade load balancer. And that will help accelerate OpenStack critical business applications. And an enterprise-grade load balancer needs to have lots of different properties for OpenStack adoption. So we need to have tenant and project isolation and SLA guarantees. And we need to have load balancer itself be highly available on top of providing high availability for the applications. And should also provide real-time visibility and analytics to basically monitor and measure your application performance and the performance of the load balancer. And any enterprise-grade ADC should have features such as SSL termination, policy-based load balancing, and so on. And as Rajiv Khanna at Expedia was mentioning yesterday in his keynote, there are many portions of the applications in enterprise cloud data center that are still running on legacy servers. So for OpenStack adoption in such enterprise cloud data centers, the solutions, the LBaaS solution, should be able to load balance not only to application components of application that are inside the OpenStack environment, but also outside the OpenStack environment. So what's the state of the current implementations? So there's the hypervisor process-based approach, such as what's recommended in the current implementation, which is HA proxy-based. And then the other approaches involve using physical or virtual appliances, which like using the traditional ADC vendors' appliances. And we argue that either of these approaches do not work well for enterprise cloud data centers. So if you consider hypervisor process-based load balancer approach, to guarantee tenant isolation and SLAs, it's a very hard problem because today, as it is implemented, it's a best effort service. And if you want to give guarantees and so on, you need to do resource limitations, resource limits on your load balancer process. How do you do that? Maybe you can use C groups and so on, but it becomes complex. And the other questions raised too, like where do you run it? Today, the reference implementation says run the load balancer, HA proxy instances on all the network nodes. But typically, network nodes and compute nodes are two different hosts in your cloud data center. So you'll have tromboning effect where packets have to travel from network nodes that are in one rack at one end of the data center to your compute nodes that are spread across your data center. If you run your load balancer agent or load balancer process on all the compute nodes, like something like what DVR does, then you run into issues like you're running some process inside your compute node, and without proper resource limits, you run the risk of overutilizing your resources on the compute nodes. So for all these reasons, we argue that it's not ideal for enterprise-grade cloud data centers. And if you look at, on the other hand, we have appliance-based ADCs, either it's virtual or physical appliances, but we argue that they are too device-centric, and that's why they're not good for your enterprise cloud data centers. First of all, guaranteeing tenant isolation and SLAs becomes very expensive. Your CapEx will be very high, because if you want high availability, you want to put one or more appliances in every availability zone. And if for guaranteeing tenant isolation, you may want to have like one or more appliances per tenant. And now we are talking about a large number of appliances that you need to get. And not only the CapEx, but on the OpEx side, you have high operational complexity and maintenance costs, because you're now doing individual device management, so that there are too many touch points. And also, many of the appliances, most of the implementation is outside OpenStack, so you need to touch the underlay. So you're doing a lot of one-off operations to set up your network, to make sure that the packets get to these physical appliances or these virtual appliances. So in contrast to the cookie cutter design in which you design your infrastructure as a service, where you're just standing up lots of racks of homogeneous servers, now once you try to put these boxes in, or the virtual appliances in, you need to do some specific network plumbing to get the packets to the right place. And overall, this basically has a limited scalability and also a very high cost, because if you have a lot of appliances, then you need to get device per device support agreements and so on. So in contrast to these approaches, either hypervisor-based, hypervisor process-based, or appliance-based, what we propose is a elastic service VM-based architecture. So what we propose is a distributed load balancer with a centralized control plane. And we propose doing the load balancing in the service virtual machines. And you can have dedicated set of service VMs per tenant, or you can have dedicated set of VMs per a group of tenants. You have a lot of flexibility once you put it into the service VM architecture. And then we propose to have a centralized controller to orchestrate and provision all these service virtual machines. And the orchestrator basically can talk to Nova and Neutron API to bring up the service VMs. So to show it pictorially, here we have the picture. And on the right-hand side, you have a controller that's basically orchestrating your load balancing and implementing it in your cloud data center. And it uses the Nova and Neutron API from the OpenStack controller. Ignore the wrapped lines. But it's basically using the Nova Neutron APIs, can do the service VM orchestration. And as you can see at the bottom, we have the service VMs that are instantiated on the compute nodes. And they can be of different sizes based on how much resources you want to give to them, or how much traffic maybe it needs to support, or what kind of computation that they are doing. And these are distributed service VMs, and you can do optimal placement. We can increase the number of VMs. We can decrease the number of VMs based on the traffic or based on the whatever SLAs that we want to provide. And we can, in this architecture, we can easily support the multi-tenant, multi-tenancy. So in this example, it's showing where the controller we can instantiate under admin. So this is one architecture, one specific architecture where the controller is also running as a VM in the OpenStack, and it's sitting in the admin tenant. And then for every tenant who wants the load balancing, we can instantiate service VMs in their context, and that gets accounted to the tenant's resources. And as you can see at the bottom in the middle for the tenant, the network that on which servers sit, we can have a network that spans the external servers too. And the service VM just needs to be plumbed to the right networks so that it can get the web traffic and send it back to the servers. And this architecture has a lot of advantages. Now, because of this simplified architecture, it's very easy to guarantee tenant isolation and SLAs. Because now we are instantiating all the service VMs in the tenant context. It's, and we can instantiate with the right amount of resources, and it's in a VM, so it's nicely resource constrained, resource contained. And we can do optimal placement of the service VMs, as I mentioned, like, so that we can place it closer to where your backend servers are. Instead of having to run, like say, in the case of hypervisor-based approach where the HA proxy was running on network nodes, in a service VM architecture, we can place these service VMs anywhere. So we can place them right on the compute nodes where a specific application backend servers are running. And we can place maybe 2 instances of your service VMs in 2 different availability zones, so you have high availability. So we have all this flexibility when we go with the service VM architecture. And with the centralized controller, we can choose a lot of different policies, and we have user-controlled policies for defining the placement and defining the resources and so on. And similar to in an SDN environment, how a centralized controller, where we disassociated the data plane and control plane made sense for L2, L3 networking. For L4 to L7 networking, we taking the similar approach by taking out the control plane and putting it in a centralized fashion. And in the OpenStack environment, as I shown the architecture, because we have this controller and the service engines, all of them running as virtual machines, it makes the installation and maintenance very easy, because now everything is inside your OpenStack. You just go through your regular Horizon UI or CLI to manage these instances. You're not going to log in into your underlying network, underlying hosts. You're not logging into your hypervisors. So that minimizes the risk to your infrastructure. And we are there are other good points for any software-based approach, which is basically we are using the same standards hardware, and that means basically we don't need any more extra spare hardware to keep around if you're using hardware-based appliances. And since we are running it as virtual machines, the network plumbing is easy. We don't need to depend on the underlay network. The network plumbing is similar to how you instantiate other regular compute VMs. You basically bring up the service VM and plug it into the right networks, and boom, you're go. You have your load balancer providing your service. And also, because it's all in the VMs, it's very easy to do scale out and scalability. For example, if you have an SSL termination, the CPU many times is the bottleneck in that case. And in that case, you can easily scale out your VMs to have multiple VMs and have another VM acting as a dispatcher to send out the request to this second level of load balancers. So that gives a nice scale-out architecture, which is possible with Service VM architecture, which is hard to do if you are in a appliance-based or HA proxy-based, where you have to pre-provision that beforehand. Whereas here, you can do it automatically as you get more traffic. So that ends my talk about the Service VM architecture. Now I'm going to invite Sean to talk a little bit, say a little bit about how to use such an architecture and use it for load balancing across OpenStack and non-OpenStack backend servers.
Thank you. Hi, my name is Sean Patronis. I work for Autodata Direct. We're based out of Florida. We deal with DMV data throughout all the states. We're actually in a migration path to using OpenStack for our infrastructure as a service. So I came to some previous summits and I met Praveen, and I was looking specifically for how to do load balancing in an OpenStack environment. So what we used to use, I should say, is HA proxy. We used Apache for our SSL termination, passed that traffic HTTP through HA proxy, and then did a lot of rules and balanced it to the rest of our cluster of servers. We have an old Zen cluster that was our virtualization platform in the past. So I had the explicit idea of coming to an OpenStack summit to just to find a solution for load balancing. I figured there had to be something, and there wasn't anything really. It was kind of tough. You have to wait for a new release, and so I ran into Praveen and started talking to him, and we started using Avi for our load balancing replacement, because I figured there's no sense of doing it outside of OpenStack. If I'm going to put everything inside OpenStack, let's use OpenStack to its fullest extent. So we've had pretty good luck with it. It's replaced our HA proxy load balancer and Apache that was front-ending it for SSL termination. We can do any of the standard rules that we can do, ACLs like you can in HA proxy. They're just way easier to configure. You don't have this mass of a config file to mess with. Adding new services is easier than, you don't have to restart HA proxy or do any funny scripts and try to restart it on the fly for any hot replacements. So it's been nice. A plus to it is the analytics that come with it. Our developers now have an easier time of seeing where maybe slowdowns in their application could be. It's been very, very nice just being able to pipe everything through it and distribute it across our OpenStack cluster. So we're in the middle of transitioning. We have some applications in production right now on it, and our old classic load balancer, that's what we're calling it now, it still has some production applications. But the beauty is I can actually load balance outside of OpenStack to my classic servers or my old infrastructure while I'm migrating things into it. So it actually can load balance directly outside. And that's been a very good benefit for us, and it'll help us in our total migration over to OpenStack and purely OpenStack in the future. So that's pretty much it. I just wanted to give you, the customers are real, and we exist. Thank you for